class now. I'm recording, and Mad Hermitian Operator. Well, hello to Mad Hermitian Operator. So let's see if somebody has a question. Questions are important. They guide me, and they inform the class. So questions play a really important role in these lectures. Let me wonder if I can move this damn screen here. Ah, there. Okay, so I hope you can all see the screen. I'm going to now go back to the beginning of Fourier Transforms and do a quick review. The basic idea is, okay, good questions. Good question about homework grades. Send an email to the grader, Evgeny, and I'm sure he'll tell you what your grade is, or I'm not sure what he's doing. Maybe I'll just ask him to send you your PDFs with comments. I'm not sure. It's a little hard to. It's not obvious how to comment on a PDF because I don't know if he has access to Acrobat. Anyhow, I imagine if you send an email to him, he will tell you what your grade is. Anyway, back at Fourier Transform land, the definitions of Fourier Transforms are like this. The function f of x has a Fourier transform, f tilde of k, and you can write the function in terms of its Fourier transform as an integral dk over root 2 pi e to the I kx times the Fourier transform. And then you can invert that, and what happens is you get the same root 1 over root 2 pi. The phase on the exponential changes, and you just change x and k. So it's remarkably symmetrical. It turns out that if we're talking about functions that are square integrable from minus infinity to plus infinity, then this map from f of x to f tilde of k is 1-to-1. And in fact, the value of the integral of the absolute value squared of f of x dx is equal to the value of the integral dk of f tilde of k absolute value squared. So it's a Fourier transforms are particularly nice in that they have this symmetry. So let's see what else I was going to say. Remember, the Fourier transform of a Gaussian is a Gaussian, and in particular, that illustrates that if the function f of x is peaked at some point, its Fourier transform typically will be spread out, and vice versa. If the function f of x is spread out, its Fourier transform will be peaked. Real Fourier transforms, the complex conjugate of a real Fourier transform is the Fourier transform evaluated at minus the argument. We went through some stuff about delta functions. A delta function of x minus y is an integral dk over 2 pi. And you get the full 2 pi here, no square roots. And then you have e to the I k x minus y. And one thing that we derived from that was Parseval's relation, which is that the integral of f star g is the integral of f tilde star g tilde. So the integral, that means that the inner product of functions is the same as the inner product of their Fourier transforms. And what that means then is that the Fourier transform is a unitary operation. It takes, it preserves the inner products. We learned something about last time about what the delta function of g of x is. It's a sum over all the points x0 that are roots of g of x, that is to say all the points at which g of x vanishes, and you divide by the derivative, the absolute value of the derivative of g at those roots. In the simple case where...
Why is the clowns in here?
Give me that again. What was that about clowns, or were you talking to somebody else? Okay, so suppose g of x is 0 only at x0. Then delta of g of x is delta of x minus x0 divided by the absolute value of the derivative of g evaluated at x0. And if it has several zeros, then you sum over them. I think there was a typo in this, and so I've corrected example 4.4. Remember, we have this remarkable Dirac-Combe relation, which is that the sum of the phase factors that occur in Fourier series is a sum of delta functions. And if you then multiply both sides of the equation by f of x and integrate over all x, what you get on the left-hand side is a sum of Fourier coefficients, and on the right-hand side, you get a sum of values of f at various points, 2 pi L. And this is called the Poisson summation formula. And the utility, as I mentioned it before, is that, as I said before, if you have a function that is spread out in x, it will be very localized in Fourier transform space, and vice versa. And so typically one of these sums converges much faster than the other. And that's something useful. Okay, let's go on to derivatives and integrals of Fourier transforms. This is important because derivatives occur in differential equations and throughout physics. So if we express f as its Fourier as an integral of its Fourier transform, then we differentiate with respect to x. X only occurs here. The derivative of an exponential is just ik times the exponential. And so we get that f prime is just an integral of ik f tilde of k. If you differentiate twice, you get minus k squared. You differentiate n times, you get ik to the n. So it's remarkably simple. You can also do indefinite integrations like this. This is my notation. You don't need to, well, might as well use it when you're studying this book, but I don't think it's caught on in the literature. Anyway, if you integrate this thing, you integrate f. When you integrate e to the ikx, you get 1 over ik e to the ikx. And in general, you get this expression. Now, you might say, well, do these converge better or worse? Well, it depends on how the function f of k behaves near 0 and as k goes to infinity. If f of k is singular in other words, if it's okay, making that PDF a little larger. Okay, so good point. You mean this one? Great suggestion. Thank you. And I can do the same over here as well. Somehow the default in the software I'm using is to make the thing too small. Great suggestion, Mad Hermitian Operator. Now, Clippy asks when homework 4 will be posted. All right, I will try to do it. I'll try to do it tonight. How's that? All right, now, so suppose f of k is big at the origin. Then when you differentiate, you get extra factors of k, but k at the origin, for small k, k is very small. So the derivatives get smoother and better defined when you differentiate. On the other hand, if f of k is big at infinity, then the derivatives are less and less well defined. Here's an example about momentum and momentum space. If you want, I will go through this in detail tomorrow, Wednesday, in the 468 class. But this is the standard notation of quantum mechanics, or the Dirac version of the standard notation. And I think the Dirac notation should be standard. I don't see there's any excuse for anything else. Another example is about the uncertainty principle. And we might do this one on Wednesday also. And so I'm deriving the uncertainty principle here. One thing that I might just mention on the fly, because it's so brief, is that if P of x is a probability distribution normalized to unity, as you would normally normalize a probability distribution, its Fourier transform is called the characteristic function. And in the language of probability theory, the expected value of a function is the integral of f of x times the probability distribution. And so the characteristic function is the expected value of the phase function. The expected value of the monomial x to the n is an integral x to the n probability, and that's a derivative of a characteristic function. There's more about characteristic functions in the chapter on probability, which chapter 15. All right, Fourier transforms of functions of several variables. It's just the same as you just repeat what you've learned for one variable. So for example, if you have a function of two variables, you use two phase factors, you integrate over both variables, you use two factors of root 2 pi, and that's your Fourier transform. If you then do the inverse Fourier transform of this Fourier transform and use the Dirac's delta function twice, what happens is you see you've got integral dk 1 and 2, dx prime 1 and 2, and you've got these phase factors. You can see then that the integral of over k1 gives you a delta function of x1 minus x1 prime. That's this one. The integral of this phase factor gives you another delta function. And since you're integrating f of x1 prime, x2 prime, you just get x1, x2, which is the natural inversion of this formula. So if the Fourier transform is this, the function has to be this, and vice versa. If you have functions of n variables, you just do it n times, and then you get that the Fourier transform of a function of n variables is by definition this, and its inverse then is by definition that. Okay, so we can also generalize the relations between Fourier series and Fourier transforms. And what we find is that the function is then a sum over these Fourier coefficients. In other words, the Fourier coefficients are 2 pi over L to the n times the Fourier transform at the particular values of k given by this. And so in particular, if f tilde is the Fourier transform of f of x, then you can write f of x as a Fourier series in this way with a 1 over v here. This is something that that sometimes one uses in quantum mechanics and quantum field theory and probably electrodynamics. Now that we know about Fourier transforms, we can use one of the Levi-Civita formulas to write any square integrable 3-vector field v of x. We'll write it as a Fourier transform, and really this works if v is square integrable in 3 dimensions. I'm sorry about this damned mouse thing. It's so sensitive. Anyway, we can let's see, I should have shown this in more detail, and so I think here in this example I've left something out. Let's go back and see whether this thing is. Oh, okay. So I added a new problem to chapter 2, and it's to derive this. So if you have any. Maybe we should pop back to that for a second, and I'll just show you what it is. If you use these Levi-Civita relations, and in particular, it's the first of the Levi-Civita relations, you can show that any 3-vector can be written in terms of any non-zero 3-vector k in this way, and so that's a. It might look like a totally absurd thing to do, but if one then uses that to write v of k in this way, then you can see that this structure here is this k here, or this k here, it can be you can get the k to occur by taking the gradient of this expression, and if you take the curl of this expression, the curl pulls down a k cross, and so this is another derivation of the Helmholtz decomposition, which says that any 3-vector field can be written in terms as the gradient of something plus the curl of something else. There's another example, Feynman propagator. I'm frankly not sure what that is doing in this particular location, but anyway. Convolutions, okay, so this is a new topic. If you have 2 functions, f of x and g of x, of a single variable, and the convolution is defined as the integral of f of x minus y times g of y integrated over y and divided by square root of 2 pi. So it's, you look at that, first time you look at that and you say, my God, why who asked for that? What good could that ever be? It's ugly as sin. Well, it has certain virtues. One is that it's symmetric. And so if you write x minus y as z, you can rewrite this as that, because then y is x minus z. And now you see this is just, you've got a minus sign here, and but you're integrating from infinity to minus infinity. If you flip from minus infinity to infinity, you then get dz. And so this is just g star f. So the convolution of f with g is the same as the convolution of g with f. Now, it turns out these things occur all the time, and we see them in physics most often in the form of three-dimensional equations, or I should say equations in three-dimensional space. And they look like this. F of x is some g of x minus x prime times s of x prime, and we integrate over all x prime. And expressions of this form are, when you have an expression of this form, you call this one here a Green's function. And it's named after George Green, who was an Englishman living at the beginning of the 19th century. By the way, Schwinger had enormous respect for George Green. Also, let me just tell you a funny story about Schwinger. In the beginning of the Second World War, he was invited to join the Manhattan Project to build a nuclear weapon. And what he realized was that that would be a long project, and he wanted to help win the war in Europe. So he said, no, thank you, I'm going to continue to work on developing radar. And he made important contributions to radar. And of course, radar was hugely important in the war in the Atlantic and in the war in Europe. Anyway, another aspect of this, you see, is that it has translational symmetry. So if you added a to x, you'd get an extra a here. But you can get rid of that a just by adding an a to x prime. So in other words, what it shows is that f of x plus a is the same Green's function integrated over a translated source. And this is called the source. Anyway, there are two examples here, which are certainly worth doing. But as I said, let's do these on Wednesday. Although if we have time today, I'm happy to pop back, and in which case I've skipped over many examples. I would like the students to say, well, do this example rather than that one, so that I know which example to do. Okay, so now one of the nice features of a convolution is that its Fourier transform is the product of the Fourier transforms of the individual functions. So the Fourier transform, the convolution of f with g, is the product of the Fourier transform of f times the Fourier transform of g. So that's a hugely convenient thing. And in as much as, you see, this is a convolution expressed. Let me just give you the bottom line of these things. The electrostatic potential at x is a constant times an integral of the charge density over everything, and then a 1 over the distance between the source and the potential, the location of the potential. Similarly, in electrostatics, if you have a current density J, then you get a vector potential that's given by an integral of the current density everywhere, and then you just weight it by 1 over the distance. All right, so coming back to this Fourier transform business, let's take the Fourier transform of the convolution. So you just do integral dx e to the minus I kx, and f star g of x, and f star g of x is this thing. And then we still have this part. Uh-oh, this says my internet connection is unstable. So students, right, I can do a Gauss law example if I have time and on Wednesday. But let me ask you guys, can you still hear me and see me and so forth? Because I've just been told that my internet connection is unstable. Something flashed on the screen saying that. So I'm just a little bit, oh, only out for a second. All right, thanks, Anonymous and Remy the Rat. I love your, the pseudonyms you have chosen are priceless. I think that's cool. So if we take that Fourier transform, what do we have? Well, first thing we have to do is we have to write f of x minus y and g of y in terms of their Fourier transforms. And so for this case, f of x minus y, you use f tilde p e to the I p x minus y, and for g of y, you just use that. And then you use your trusty delta function formula. So we've got a dy, dx, dp, dq, the integration over x, we have e to the minus I kx, e to the plus I px, so that gives us a delta function of p minus k, and takes away a factor of 2 pi. And then we have an integral of y here, I q minus p, that gives us a delta function of q minus p and gets rid of the other 2 pi. And then if we just do the p and q integrations, p gets set equal to k, q gets set equal to p, or let me say that again. Yes, p gets set equal to k, and then q gets set equal to p, which is k, and so we just get f tilde of k, g tilde of k, which is this expression here. So we've derived the Fourier transform of a convolution as a convolution of the Fourier transforms. So now, let me just show you how easy it is to do, to find Green's functions for linear partial differential equations. So first of all, a Green's function for a particular differential operator is something such that if you use p to act on the Green's function, you get a delta function. And in particular, if we're talking about x of n variables, then it's a delta function of n variables. And now, when is this? I just said all this is pretty easy. Well, it's easy when this p, this differential operator, is just a polynomial in the partial derivatives. So because then we have the equation p of the partial derivatives on g is the the delta function in n variables of x. And now if we express both of these as Fourier transforms, we get p of delta on g of x. Well, g of x is this e to the I kx g tilde of k. This is the Fourier transform of the Green's function. But the derivatives, each derivative pulls down, the derivative with respect to x1 pulls down I k sub 1, and the derivative with respect to x3 pulls down I k3, and so forth. So what you get is you just replace p of delta with p of ik. And we want that to be the nth order delta function, or the delta function in n variables, and that's an integral dnk over 2 pi to the n e to the I kx. And so we've got just a simple equation here. We've got the e to the I kx here and here, dnk, and then we've got p of ik, g tilde of k equals 1 over 2 pi to the n. So g tilde of k is just 1 over 2 pi to the n, and you just divide by the polynomial in ik. And so bingo, you've got the Green's function for infinitely many partial differential equations in any number of variables. And so this is one of the reasons why people love Fourier transforms. You can get Green's functions very quickly, very easily. Here's an example that occurs a lot in physics. The Yukawa differential operator is minus Laplacian plus the square of a mass. And we want to find a Green's functions such that minus Laplacian plus m squared turns the Green's function into the delta function. And well, what's the recipe? Well, you just divide by, you convert this thing to a polynomial in ik. And so this is minus grad squared. So this thing will have to be minus ik squared. And ik squared is k squared. So minus ik squared. I'm sorry, ik squared is minus k squared. And so minus ik squared is k squared. And so you get k squared plus m squared. So you get this nice integral. And that integral is what's called a Yukawa potential. It's like a Coulomb potential, but it has a fall off at short range. So it makes the force of short range. And this is something that is generally true, namely that if a particle of mass m is communicating a force, then then the force falls off as e to the minus the mass of the particle times the distance divided by 4 pi r. So in the case of a photon, the mass is 0, and so e to the 0 is just 1, and you just have 1 over 4 pi r. And now Laplace transforms. So the definition is that you just integrate from 0 to infinity. You don't integrate over the whole real line, you integrate only over the half line. And then instead of a phase factor, you have a decreasing exponential. Now, the advantage of Laplace transforms is that you don't need f of t to be square integrable. F could be t squared, and you'd still get a Laplace transform. And the reason is that this exponential means that as long as f of t does not increase as fast as it does not increase exponentially fast, then it has a Laplace transform. So that's the basic advantage of a Laplace transform. But apart from that, the Fourier transform has, I think, far more uses than Laplace transform. Anyway, and as S increases, if S is real, this becomes smoother and smoother, and you can have wilder and wilder functions f of t. And so as an example, suppose f of t is just 1. So if f of t is just 1, then its Laplace transform is just the integral dt of e to the minus st, and that's just 1 over s. On the other hand, the function 1, it has a Fourier transform. That's a delta function, so it's not a square integral function. The function e to the kt diverges exponentially if the real part of k. Yeah, in general, we're going to be talking about complex numbers. So k is complex here. So it diverges exponentially if the real part of k is positive. And the Laplace transform, well, it's like that, and it's 1 over s minus k. So it's well defined for when the real part of s is greater than k. On the other hand, you can say, well, this is what it is for s greater than k, and this is a perfectly nice function for all s. So you can think of this as it's called the analytic continuation of the Laplace transform. So initially, the Laplace transform is defined just for real k greater than I'm sorry, for real s greater than k. But once you've realized what it is for s greater than k, you can say, well, hell, I'll call the Laplace transform of e to the kt. I'll call it this for all s. Examples of Laplace transforms of cosh, it's s over s squared minus k squared. Sinh, it's k over s squared minus k squared. Cos omega t, it's s over s squared plus omega squared. Sinh, it's omega over s squared plus omega squared. All right, I'm certainly going to skip this biophysics example. If you're interested in biophysics, read the example. Now, how do we invert a Laplace transform? Well, once again, Dirac comes galloping to the rescue. What will we do without Dirac? We'd actually be in a big trouble. Anyway, what do we do? So here's our function f of s, and we want to find out what is f of t? In other words, how do we find out, if we're given f of t, we can take its Laplace transform and get f of s, but what if we've given f of s, how do we find f of t? And so what we do at first is we make s a complex variable. So we let s be real and we add iu. And so then we've got this expression here. And the next thing we do is we say, well, we're going to make s big enough so that f of s plus iu is suitably smooth and bounded. And then we're going to take a Fourier transform of s plus iu. So we're going to multiply by e to the iut, integral du over 2 pi, f of s plus iu, and so then we get this expression here. Now, here what we have, you see, is we have an integral du, we have e to the iut, e to the minus iut prime. So we have this expression here, and what's left over is the integral dt prime of f of t prime. And now this, of course, is the delta function of t minus t prime. So that gives us this. And now we do the d prime into the dt prime integration, and we get e to the minus st f of t. So that's how you invert a Laplace transform. So your function f of s is the Laplace transform of something, and that something is e to the st and integral du over 2 pi to the iut f of s plus iu. And notice that s is not occurring on the left. So the behavior, the dependence of the right-hand side on s has to cancel. And I must say, just looking at it now, I'm a little surprised. I'm going to have to think a little more about this to understand why it's obvious that the s dependence cancels. What you do, though, is you pick s to be big enough so this integral is well defined. And here's an example. So suppose f of s is 1 over s minus k. Then applying this recipe, you have the e to the st here to the iut there, and now f is 1 over s minus k, so we have 1 over s plus iu minus k. We do the u integration, And bingo, that gives us e to the kt without any S dependence. So it actually works. So what's lying behind this, you see, is some complex variable theory. And that's why in most books, one might put linear algebra in chapter 1, but one typically puts the Fourier transforms back in some chapter 7 or something after complex variable theory and so forth. But as I said, I think that if you're studying physics, you need to know more about you need to know more about Fourier transforms. You need to know something about Fourier transforms at the beginning of your studies because they pop up all over the place in physics and quantum mechanics, electrodynamics, and so forth. Volterra introduced a convolution that is more suitable to the Laplace transform, that's suitable to the Laplace transform. And so I'm writing it as F star G, and it looks like that. What about derivatives and integrals of Laplace transforms? Well, you differentiate n times, you bring down minus t to the n. And these are then usually well defined because of the exponential. So for example, if f of t is 1, then the nth derivative is just n factorial over s to the n plus 1. And you can also imagine differentiating f instead of differentiating f with respect to t instead of differentiating little f with respect to s. I should have used different labels here because I have to say f and f. In any event, once you have f prime, you then rewrite that in this way as a derivative of e to the minus st times f minus f times the derivative of e to the minus st. And so that gives you this evaluated at the 2 points. Well, for t equal to 0, you get minus f of 0. For t equal to infinity, I'm assuming here that vanishes. And what's left then is this, the integral of this, and the derivative there pulls down a minus s, and so we get this expression. On the other hand, that is just f of s. So basically the Laplace transform of the derivative of capital F is s times the Laplace transform of capital F minus capital F at 0. And you can also indefinitely integrate the function f. And if you do that, you integrate with respect to s, you pull down a minus t, and you integrate n times, you get something like that. Okay, Laplace transforms and differential equations. So this is like what we did for Fourier transforms, but it's a little different. So suppose we have a polynomial in derivatives with respect to s on f of s equal to j of s. So we write j and f both as Laplace transforms, and then we take p of d by ds on f, and that will give us each derivative will turn with respect to s pulls down a minus t, so we get p of minus t f equals the Laplace transform of j, which is e to the minus st j of t dt. So that tells you then, that gives you an algebraic solution, namely that the Laplace transform of f is the Laplace transform of the source divided by the differential operator evaluated at minus t. And so what that says is that if we have this differential equation, a particular solution of this inhomogeneous differential equation is this. Now, this differential equation is said to be inhomogeneous because there's a j here that's not zero. The associated homogeneous equation is the same thing with j equal to 0. And one way of writing a solution of the homogeneous equation is to just write it as a delta function like this, where capital H is arbitrary, but we've got here the delta function of the differential operator evaluated at minus t, because then when p of d by ds hits this, we get p of minus t delta of p of minus t. Well, the delta function says, okay, evaluate, this integral is equal to e to the minus st h of t, p of minus t, evaluated at points where p of minus t vanishes. But that's 0 because p of minus t vanishes there. This is as long as h is suitably smooth. And so you can write the solution of the inhomogeneous equation, this one, as this. So the solution of this then is this particular solution of the inhomogeneous equation plus this solution of the homogeneous equation where h is quite arbitrary. So this gives us a whole class of solutions of this differential equation. And if we apply that to a differential equation in n variables, we have p of the derivatives we have p of the derivatives on function of n variables is g, some inhomogeneous term, a source term. And we write both as, well, here I'm writing them as Fourier transforms, but what I'm really doing is I'm saying, let's use whichever works. So in other words, these are going to be, we're going to integrate over real K. We're going to try integrating over real K. So then we're expressing F as a Fourier transform. But may be that F tilde is such that we're better off with Laplace transforms. In the case of Laplace transforms, we integrate each K from 0 to infinity up the y-axis of the complex plane. So these K's are, this is, K is I times something that you're integrating from 0 to infinity. And so we know that the nth derivative with respect to xj is the nth power of ikj. And with a couple of abbreviations, we then have p of the derivatives on f is f tilde p of ik. The ik is the Fourier or Laplace exponential dnk. And that has to be g of k times the same thing. So the inhomogeneous partial differential equation becomes an algebraic equation in K space, and a particular solution then, as with the case of Fourier transforms, is the transform of the source. Transform of the source divided by the differential operator evaluated at ik, And then this factor, which is a phase factor if we're doing Fourier transforms, or something that might have some Laplace terms in it if we're using Laplace transforms. And then the space of homogeneous solutions, as I said, is huge. And I'm going to use the same trick as before, and I'm going to take an arbitrary function of k variables just as long as it's smooth, and then I'm going to write the homogeneous thing as the transform factor delta function of the polynomial in the ik's times the arbitrary function h. And so the general solution then is f of x is this, the transform factor, the ratio for the inhomogeneous solution, and then this arbitrary, this term here, which vanishes. I mean, it'll be such that when P hits F, you get P of ik, delta of P of ik, h, and that's 0 when you integrate it. So here are a couple of examples of that, and as I said, Wednesday is a good time to do that. By the way, in quantum field theory class, one sort of plops down the answer, but if you use these techniques, you'd actually derive the expansion, the conventional expansion of a scalar field, or a vector field for that matter. There's an example of diffusion. So if you're interested in biophysics, read this example. Okay, so we're done with the exposition for chapter 4. I'm not going to start 5 today, but we've got something like 20 minutes or 25 minutes to play with examples. So let's use the chat function and tell me what you'd like me to do. Now I see there's one request already from the mad Hermitian operator to use the example, the Gauss's law example. So let me flip back to that if I can find it. It wasn't yeah, it was convolutions. So let me pop over to convolutions. So is this the example that mad Hermitian would like me to redo, the one using Gauss's law? This is Gauss's law. Remember, the more responses from the class in terms of chat and I wish we didn't have this stupid FERPA crap. Oh, by the way, I have added some examples to the example PDF, and one of them is right here, a 3D delta function, delta of x minus y is either plus or minus I, x minus y dot k d cubed k over 2 pi cubed, and in n dimensions, it's just 2 pi to the n dnk, and same dot product. This is a delta function in n variables. This is in 3 variables. Sometimes people write parenthesis 3, close parenthesis, parenthesis n, close parenthesis. All right, so 411. Okay, thank you. Sephiroth. Okay, that must mean something, but I don't know what it is. Anyway, so Gauss's law, the divergence of the electric field is the microscopic charge density divided by the electric permittivity of the vacuum. That is to say, del dot E is rho over epsilon 0, Gauss's law. Notice that this is a constraint. And it's something that is skipped over in most physics courses, undergraduate and graduate. And it's really a pity because the constraint shows up here as one of the basic features of electrodynamics. And if there's any part of physics that's well known, it's electrodynamics. Anyway, if the charges and fields are independent of time, then the electric field is just the gradient of a scalar potential. And if you combine these two, so this is the thing that's absolutely general. Del dot E is rho over epsilon zero. That is generally true. So you let E equal to minus grad of some scalar potential. And notice what we're doing here is we're in a sense using the Helmholtz decomposition because we know the electric field is the gradient of something plus the curl of something else. But if the charges and the fields are independent of time, then you can drop the curl expression. And so you can just get away with E being minus the gradient of phi, and combining the two, you get E minus Laplace minus grad squared phi is rho over epsilon zero. My dog, I think, has seen another dog and is barking. We can solve this equation by using Fourier transforms in the way that we just described, namely that we write phi as a Fourier transform. We hit that with minus grad squared and we get a k squared. We want that to be rho over epsilon zero. So we write that as a Fourier transform. Now we compare the two, and comparing the two, you see that phi tilde has to be rho tilde over epsilon zero k squared. And so that means that the Fourier, this is that the Fourier transform of the scalar potential is the product of the Fourier transforms rho tilde and 1 over k squared. And here you might say, well, what is that? What is 1 over k squared? Why is 1 over k squared a Fourier transform? Well, the idea is that minus Laplacian inverse, is essentially 1 over k squared. Let me just sort of show you that, although, in other words, the Fourier transform of the inverse Laplacian is 1 over k squared. So you can think about that if you want. In any event, what we get is that phi tilde is rho tilde over epsilon zero k squared. And so now we have a formula for the scalar potential. It's e to the I k dot x, phi tilde is rho tilde over k squared. And so now, what do we have? Well, what's rho tilde? Rho tilde is the inverse Fourier transform of the charge density. So we've got an expression like this now. And so rewriting that, we have the rho tilde, rho of x prime. This is the source, the charge density over epsilon zero, and everything else we call g. And this is the Green's function. G is an integral d cubed k over k squared e to the I k dot x minus x prime. So this is the Green's function for this differential operator. And the sense in which, so 1 over k squared is the Fourier transform of g. And on the other hand, minus Laplacian on G is the delta function. And so, in a sense, this G is the inverse of minus Laplacian, because the delta function is like the identity operator in position space. And all right, well, anyway, I think I should stop all these asides that are somewhat beside the point and hard to understand. Oh, here I say it, G is the inverse operator minus Laplacian. Okay, so what we have then is that G of X is given by this integral. And if we do the integral, well, you can just follow the steps here, the phi integration, the integration around the axis defined by x minus x prime. The phi integration just gives 2 pi, so 2 pi cubed goes to 2 pi squared. You then integrate d cosine theta on this, and you get this expression. This is a sine, so we get this. And this is a non-trivial integral, but we'll see when we study complex variable theory that this integral is actually just pi over 2. And putting it all together, then we get that the Green's function is 1 over 4 pi x minus x prime, which of course you learned in undergraduate E&M. And so the scalar potential is 1 over 4 pi epsilon 0, integral of the charge density divided by the distance. And in the case of the static magnetic vector potential, we have the same business. But I mean, I can just go through this example also, but maybe there's a question here. So would somebody like to ask a question or to point me to a different example? Would you like me to go through something else, like the uncertainty principle, or the example from biophysics involving diffusion? So I need help. I need somebody to say, do this, and then I'll do it. But I'm not a great listener. I can't read minds at all, and I certainly can't read minds at a distance of a mile or so. So I don't know what you would like me to do. So let me just sort of pace through some of these things. Let's see if I can find some nice examples to do. You must have seen the uncertainty principle several times, so maybe I'll not do that one. Well, let me pop over here and to the very last example. I think this might be amusing to people. It's some biophysics. And by the way, let me just mention to you guys that biophysics is a very good field to get into, because there are lots of jobs in the field, and the work that you do as a biophysicist is typically something. It has typically something to do with advancing medicine, and if there's anything we want, it's advancing medicine. And we have a small biophysics group at UNM, and so I recommend that you think about doing biophysics. You might say you don't know any of the biology. Well, biology is something you can pick up on the street. It's really, compared to theoretical physics, it's like eating popcorn. Okay, so let's think about a flow rate J of a fixed number of randomly moving particles. And how will they be moving? So this is, they're diffusing. We're not talking about turbulence. So the flow rate J is some constant times minus the gradient of the density. So obviously, the denser the concentration of these particles, the faster they're going to move away from that point. Or I should say, anyway, it's clear that something like this is right. And on the other hand, the number of particles is conserved. So this 4-vector J, rho J, obeys a conservation law, namely the time derivative of the integral of the density of particles is minus the flow rate integrated over some surface. A surface containing the area, the volume on which you're integrating here. And but that surface integral is minus the integral of the divergence over the same volume. And if we now combine that with this thing, which is called Fick's law, what we get is that rho dot is minus the divergence of J. On the other hand, J is minus D gradient of rho. So this is D gradient squared of rho. Or putting it all together in one expression, we get D times gradient squared is minus the time derivative. Minus the time derivative acting on rho gives you 0. And Fourier was thinking about, in fact, I think Fourier invented his transform in order to solve equations like this. Glauber told me that once or something like that. I might have forgotten exactly what he said. Anyway, the density rho of x and t, we're going to write it as a transform. And I'm not saying whether it's Fourier or Laplacian or Laplace at the moment. And we're going to act with the diffusion equation. We want that on rho to be 0. And so we want this structure to be 0. So we've got an algebraic equation like that. And this is then a homogeneous equation. And we learned one way of solving homogeneous equations is you just take an arbitrary function h, and you then take delta of the differential operator and your transform variable, and you write this as this gives you a class of solutions of the differential equation. Now, the delta function here requires omega to be imaginary, because otherwise, I mean, this is real, so omega's got to be imaginary. So the omega integration has to be up the imaginary axis, and that means it's a Laplace transform. And so if we do the omega integration up the imaginary axis, it just changes minus I omega into, or changes I omega into minus d k squared. And so we get the delta function converts the exponential to this expression. So this is our solution. And notice that rho tilde is arbitrary. Why is it arbitrary? Well, it's this arbitrary function that we introduced. And why is it arbitrary? Well, because we're talking about a general, we're just looking for the general solution of the diffusion of Fick's equation. In other words, a general solution of diffusion problems. And so what does that tell us? That tells us if rho tilde of k is the Fourier transform of the initial distribution of particles given by this equation, then the Fourier transform rho tilde is this. And so you can express rho of t as this. So in other words, I've taken this rho tilde of k, it's e to the minus I k dot y over 2 pi given from this boundary condition. And so what we have then is that the density at time t is, well, let's see, I have, yeah, I forgot to mention this, namely that the initial density, we're concentrating the initial density at y. So if the initial density is at y, then it's a delta function, and its Fourier transform is then that phase factor. And so then we get this expression that if at time 0 you have a density that's infinite at the point y, then at later times the density at x is e to the I k dot x minus y minus d k squared t d cubed k over 2 pi cubed. And on the other hand, this is the Fourier transform of a Gaussian. We know what it is, namely it's given by 4.19. That gives us this. And so the solution then is a decaying exponential, an exponential Gaussian, in fact, and 1 over t to the 3 halves. And since the thing is linear, we can imagine an arbitrary initial distribution. So if the initial distribution at time 0 is rho of y and 0, then at time t, the density at x is given by 1 over 4 pi dt to the 3 halves, and then e to the minus x minus y squared over 4 dt times the initial distribution integrating over d cubed y. Okay, so that's another example. This is biophysics, and it shows that it suggests that all of this is actually useful. Namely, we have ways of solving partial differential equations very easily, and these are correct solutions. But let's see, though, maybe someone would like to, we've got only 2 minutes left, so I don't know if I can do another example, but I can answer a question. If somebody has a question, simple questions are preferred, hard questions are acceptable. So let's think, do we have any questions? Would be well, maybe I'll just say something about this example here, since nobody's told me what to do. So we can write if we have a wave function psi of x, its Fourier transform, we can write this way. And what happens in undergraduate physics classes is we typically switch from k, which is a nice variable, to momentum over h bar, and then we've got these h bars all over the place, and it's just so awkward. This is why many physicists do calculations in units where h bar equals 1. Because then there's no change between these two equations. All right, well, we're basically out of time, so I think I should stop. Till tomorrow and at 5:30, and tomorrow do come with questions, and not simply questions, but also let's see, what shall I say? Examples that you'd like me to do. So we've gone through various examples, and I've skipped over a lot of examples in the chapter on Fourier transforms and in earlier chapters. And so if you say, well, I'd like to see you do this example, then I know what to do. Whereas otherwise, I'm not sure what to do. All right, so I'm going to stop the recording. Let's do that first. Okay.